the final chapter. We talked about equilibrium last time. And as we talked about, it does involve really a certain type of reaction, which is a reversible reaction. Again, those guys basically heading in both directions. Again, there's a forward direction, which basically means that we're going to go from reactants to products and make more products. There's also at some point when the products sort of get enough made, they will decide to kind of come together and the opposite reaction will happen, basically the reverse reaction, where the products will kind of break back apart and go back and make some more reactants. When we do reach chemical equilibrium, as we talked about, it is the idea of really the rate of the forward direction will equal the rate of the reverse direction. Remember that chemical equilibrium doesn't necessarily mean that you have the same amount on both sides. What it means actually is the rate. As quick as it goes to make products, those products will sort of recombine and make the reactants. So really what happens is everybody gets locked into place in terms of where they happen to be at that moment in terms of their concentrations. They basically will be able to maintain their concentrations, because as fast as they lose a little, they will basically gain it back just as quick, and they're able to really maintain where they're at. If we're dealing with gases, they also could be maintaining their pressures on both sides, but in terms of concentrations. So that is what chemical equilibrium really means. Again, sometimes people think, well, it just means like it's equal on both sides and everybody's all equaled out. But again, it's really the rate of how quick it's going in one direction versus how quick it's going in the other direction, and they equal each other. There is a relationship that's known as the equilibrium constant, which is capital K. And K is calculated by taking the concentration of our products divided by the concentration of our reactants. And remember that concentration, for the most part, means molarity, which is our moles per liter is what we're talking about here. And it is important, though, that we do take the coefficients into account. So if you do have an equation like this, we do want to take the coefficients there. And they become really our exponents when we do our equilibrium constant. Is C to the C, D to the D power, A to the A, and B to the B. Now, when we do this, K is just a number. And as we talked about last time, if you have a large value of K, that means that when you reach equilibrium, you should mainly have products present. Again, to get a large value, mathematically speaking, you got to have a large number up on top, small number on the bottom, means that you will get a large number. If you have a small number or value of K, that means when you reach equilibrium, you will have mainly reactants present. Same idea, to get a small number, you need a larger number on the bottom there, which are reactants, than our products. Remember, the big giant number of 1 is considered large, so anything above 1 is considered large value. Anything less than 1 for the equilibrium constant is considered a small value. There is various degrees of large and small. There are some equilibrium constants that are like times 10 to the 52, and there's some that are like times 10 to the minus 34, which is super, super small. So there are some sort of various degrees and anywhere in between there. But really, the value of K does give us information about when we do reach equilibrium, and that rate of the forward reaction equals the rate of the reverse reaction. You know, would we mainly have more products or reactants there that are present? Now, in addition to that, there are a couple of things that we do not include in the equilibrium expression, and we do not include anything that is a solid or a liquid. So anything that is a pure solid or liquid does not get put into the equilibrium expression, and that's because they basically are pretty much constant throughout the whole ordeal here. They're really not changing, so they don't really participate in equilibrium. That pretty much leaves us two things that we do include, and those are things that have the aqueous symbol or the gas symbol. So those are the two things that we do put in there for sure. The other important thing about the equilibrium is this: it is a constant value for a particular temperature. So as long as you do not change the temperature, you will always end up with the same equilibrium constant. For example, if you did one reaction like one you did the other day, where like the iron and the thiocyanate that made the blood red complex ion there. If you did that reaction, you started with all reactants and let it go to equilibrium and calculate the equilibrium constant. And then you did that reaction, you had a little bit of reactants, maybe a little bit of products there, and you let it go to equilibrium and you calculate the equilibrium constant. Or you had maybe all products and you let it go to reactants. It would always end up at the same number for the equilibrium constant. So the proportion of products to reactants, even though they may be different numbers, will always end up at the same number as long as you do not change the temperature. So you may be saying, I'm not really sure about that, because, you know, if we wanted a number like 2, there's many different ways you could get to 2, right? You could have 4 divided by 2 gives you 2. You could have 8 divided by 4 gives you 2, right? So there's many different ratios that will end up at 2. If you just want to take a simple example, and that's sort of what happens with the equilibrium constant. Although you may start with different amounts, the proportion of products to reactants will always end up being the same proportion and will always yield you the same value for the equilibrium constant, regardless of how much you start with. So sometimes people think, well, I started with way more reactants in this reaction than the first one, I should get a different value of the equilibrium constant, and that's not what happens. Again, it will always end up at that same proportion. Now, in addition, we also talked about something, I don't know. We talked about Le Chatelier's principle, which basically is the idea where you have a system at equilibrium and you do something to it to basically mess it up. So let's talk a little bit about that. We'll kind of pick up where we left off, or maybe review that along the way here. But any questions on this stuff here? Again, just a reminder that it is temperature that's the only thing that affects the actual value of the rate constant. I'll get to your question in one second. So when we talk about if you calculated a value of K, I say 25 degrees Celsius, and you did the same reaction, but it was done at 40 degrees Celsius, the values of K at each of those temperatures would be different. But if you kept the reaction at 40 degrees and did the reaction 3-4 times, and you calculated the equilibrium constant, it would always end up the same number at 40 degrees, just like it would always end up the same number at 25. But as you change the temperature at each, the value of K at each temperature will be different. Defining, we're actually going to do some examples today on it. Yeah. Yep. Other questions? Okay. So let's talk about Le Chatelier's principle. Remember that this is where you have a system that is at equilibrium. And basically you do something to it, like you add a stress to it. And remember that some type of stress could be something to do with the concentration. It could be something to do with pressure or volume. If you're dealing with gases, it could do something with temperature. It could also do something with like a catalyst, for example. So what happens though is you add a stress to the system and pretty much you mess it up, right? So what that means is it is no longer at equilibrium. So the rate of the forward reaction and the reverse reaction will not be the same. The reaction itself is going to want to basically self-correct. It's going to want to get itself back to equilibrium. So it'll basically do one of 3 things. It will either shift to the right, which means it will make more products. It will shift to the left, which means it will make more reactants. Or there are situations where even though you kind of did something to it, there's going to be really no change that's going to occur. And we'll talk about a couple of these here as we go through it. I think last time we talked about concentration, and I think I drew my wonderful stick figures, I think last time, right? We did some concentration. And when we do add concentration, it always shifts away from the side we added it to. Now, clearly, there is no side in a beaker or a test tube, right? You know, basically, because it's an equilibrium expression or reaction, you got everybody floating around in there. So, for example, you know, you got your iron 3, you got your thiocyanate, you got your complex ion floating around in there. You got everybody basically floating around in there. So when we talk about left and right, we're really talking about the balance equation, left-hand side or right-hand side of the balance equation. Either you added more reactants or you added more products. When you add, it will shift away, and when you remove, it will shift towards the side. Remove. So add away, and when you remove, it goes towards it. So for example, you guys did this, I think, the other day. And this is like red, and then maybe this is maybe a yellow type color. So for example, if you added something to it, like iron 3 nitrate, which I think was one of the guys, you are basically want to think about what you're adding. This is basically a source of iron, and it's a source of nitrate ions. Basically, it's the two things. Nitrate is nowhere to be found in this reaction, and frankly, it's not going to really react with anything because it's soluble and everything. But we do see iron that's present. Iron 3 is on the reactant side. So really what happens is when you add iron 3 nitrate, you're really adding more iron. And when you add more iron, that means that there's a lot more reactants available to start reacting. So when they start reacting, that's going to cause the forward direction of this reaction to take place. And you should hopefully see it maybe turn a little darker red there, blood red. And that's because it's going to shift away from it, because basically you added more reactants, and that's going to kick off the forward direction of this reaction to occur. And so that's why we say add away, because it will always go away from whichever side you added. If you added more products, it would shift to the reactant side to do so. When we remove something, we talked about that there's really kind of two ways to remove something in a solution. And basically one way is to make it precipitate or a solid, or you can make water. So for example, if you had something like actually that equation right there that we had. And you decide to add a little silver nitrate to the action here. This would actually give you some silver and some nitrate. Once again, neither one of these guys are actually in this reaction. But the nitrate's soluble in everything. But when you would add silver, it actually would go and react with the thiocyanate, and it would make silver thiocyanate, which is actually a solid. You would actually see a white solid that formed. When that white solid formed, that would mean I would essentially be making a precipitate and removing my reactant side. Basically got a hole on my reactant side. What that really means is I have a lot more products now available in that beaker, and that's going to kick off the reverse reaction to occur. And that's going to cause it to shift away or shift towards the side I removed it from. And that would cause more reactants to be seen. And if you did this, it might be hard to see because you have a white solid in there, but you would actually become a little bit more yellow in that case because of that. So that's a very common way that you could remove something from solution, is to add something that's not there, but if it did react, it would maybe make a precipitate. The other way is if you have hydroxide or even H+, you could add an acid or a base to that and make water. So for example, I think you did the one with chromate that had hydroxide on one side. And if you first added a bunch of sodium hydroxide, which is a source of sodium ions and hydroxide ions, that means that you're adding more reactants, going to kick off the forward direction and cause more products to be made. And you would see it go, I think it was orange maybe on that side of the reaction. Then you added to the same reaction some hydrochloric acid, which is basically a source of H+ and Cl-. By adding H+ and Cl-, it wasn't in the equation, but the H+ and the OH- will come together to make water. And that is basically removing water in that, or hydroxide in that case. And that would cause the equilibrium to shift towards the reactant side. And you saw the color come back the other way, basically by adding the acid. So when you do make water, it is sometimes hard to visually see water unless you're doing something where there is colors on one side or the other that you could kind of see it occurring. But that is a very common way that you could remove something from solution. Any questions on any of that there? All right, the next sort of Le Chatelier's principle has to do with pressure and volume, and they are oftentimes tied together. And a lot of times, this is usually involving gases. And when we think about pressure and volume, we think about P1 V1 equals P2 V2, our good friend Boyle. And the relationship that we see in Boyle's law is as the pressure goes up, the volume goes down. So in this particular case, what would happen is if we decrease the volume or increase the pressure, the volume would get really small, which means my gas molecules are pretty much really near each other. And that's why the pressure starts to go up. So the change that we want to do actually is to bring the pressure kind of back down. So the change that was occurring is coming up. We want to kind of bring it back down. So to bring the pressure back down, would we need more or less gas molecules in that very small area? If I put more gas molecules in that small area, the pressure would continue to go up, right? So it actually need less gas molecules in this small area, and it would shift to the side with the less gas molecules. And that's hard to say left or right. It is dependent, obviously, on the equation you're looking at as to which side has the least number of gas molecules. And the opposite would be true if we decrease the pressure, increase the volume. Now our gas molecules have a lot more room to fly around in. What we start to see is the pressure starts to come down. So we want to kind of bring the pressure back up. So to fill that space, we actually need more gas molecules in this case. I personally look at volume in this situation, small volume, less gas molecules, larger volume, more gas molecules. That's a good way to remember it. Any questions on that there? So if I had something like 2A plus B goes to 6C here, and they're all gases. Let's say I added more C, I removed A, I increased the volume. So take a moment, will it shift to the left, right, or will there be no change? Okay, let's take a look. So we're gonna add more C, so C is over here. So we're adding more products, add away. What's really happening is we're making a lot more products available to each other. That is gonna kick off the reverse reaction. So it will shift away from the side we added it to. We're going to remove A. A is over here on the reactant side. So again, as you remove A, kind of like a hole on the left-hand side there, that also means really there's a lot more products available in that solution. And that also will kick off the reverse reaction and head towards the side that we removed it from. When I increase the volume, that means my pressure will start to drop. So to bring my pressure back up, in the larger volume, I need more gas molecules. And in this case, it is as simple as counting the coefficients. That is 3 for each of those things that are gases, and that is 6. So it should shift to the right in this case. Any questions on any of those there? So pressure and volume, oftentimes seen with gases. Like I said, I personally would kind of look at the volume aspects of it: small volume, less gas, more volume, larger gas. The next thing is actually temperature. And the good news about temperature is it works the same as concentration, which means if you increase the temperature, it's going to shift away from the side. And if you decrease the temperature, it's going to shift towards it. So how do I know which way it's going to really go? It does depend on what type of reaction you're dealing with. If you are dealing with an exothermic reaction, that means heat and energy is released. What that means in terms of an equation is we consider basically heat and energy as a product. So it's basically a product in this case. That means if I increase the temperature of an exothermic reaction, it's going to go away, which will send it to the reactant side. And if I decrease the temperature of an exothermic reaction, it will come towards the side that it's on, which would be the product side in this case. Opposite is true for endothermic. Endothermic means that heat and energy is absorbed. And that means that heat is considered, heat or energy, a reactant in this case. So if you have an endothermic process, if you increase the temperature, it will actually shift away from it and make more products. If you decrease the temperature of an endothermic, throw all your test tubes on ice, it will remove the heat and energy from the reactant side and it will go towards it. More often than not, energy in a reaction is given by delta H. If you remember, that is our enthalpy, our heat of our reaction. Pretty much all energy values that are negative are exothermic. So very common, delta H will be given to you and it's a negative value. It's an exothermic reaction. If delta H is given to you and it's a positive value, it is an endothermic reaction. And that is more often than not how it is sort of displayed to you in a Le Chatelier's principle type question. They give you the equation and they say, hey, the delta H of this one is like minus 336 kilojoules. The number really doesn't matter. It's actually the negative or positive matters in this instance of determining if it's exothermic or endothermic. Any questions on that there? Now, last couple of things that can sort of affect it, not really, are a catalyst. A catalyst, again, is not a reactant. It's not a product, and it does not get used up in the reaction. It basically is just there to speed up a reaction in most cases. Most of the time, catalysts are written like on top of the arrow. So something like platinum or H plus or something like that's written up on top. Now, how that affects the equilibrium here is it actually has no change. So it will have really no effect on the equilibrium. Another way that you could kind of get a no change is to add some type of like noble gas, like helium or neon or argon. Because they're chemically inert, they really won't participate. And that's another way to get kind of a no change situation. Any questions on that there? So let's say we had our imaginary 3A plus, we'll go with 2B. Gives us 3C. All right, so let's say our delta H here is plus 135 kilojoules. And let's say that we want to know, will it go to the left? That's not how you spell left. Will it go to the left? Will it go to the right? Will there be no change? If I increase the pressure, if I add more A, if I decrease the temperature, if I remove B, if I increase the volume, and let's just say I added like a catalyst. All right, so for each of these, should it go left, should it go right? Will there be no change? See what you come up with here. Okay, let's take a look. So we're going to increase the pressure, which means really the volume is going to come down. So really in a small volume, I want more or less gas molecules. In a small volume, I want less gas molecules. In this case, that's 3 and 2, which is 5. This is 3. That means in this case, we will shift to the right-hand side, which has the least number of gas molecules. Excuse me. Any questions on that one there? Going to our right, we're going to decrease the temperature. So this reaction is endothermic because I do see a positive sign there. That means if I added heat to the equation, it would be a reactant. So in this case, I'm going to remove heat, which is going to cause the equilibrium to shift towards it. So it will shift towards the side I'm removing it, and it should go to the left. Any questions on that one? If I increase the volume, I then want actually more gas molecules in this case because my pressure will start to decrease. And that means in this case, we calculated earlier, we need to shift to the left in this case. If I add more A, I have more reactants, which will kick off the forward direction. And when it kicks off the forward direction, it will shift and make more products in this case. And we should shift to the right. What happens if I remove B? Remove B, it should go which way? It should go to the left. When I remove B, it's kind of like a hole on this side. So you can think of it as it needs to fill the hole. So it'll go towards the hole. Or really what's happening is because you have less reactants, you actually have more products. And that's going to kick off the reverse reaction, which is going to head it that direction. So it will go towards where we removed it in this case. Lastly, adding a catalyst here will cause no change basically to occur. You will just get to the equilibrium faster. Any question on any of those there? Now, by the way, there is a, let's say we had something like this. And I increase the pressure. Which way will it shift in this case? It would be no change in this case because we increase the pressure. That means we want smaller volume. We actually want the smaller number of gas molecules. In this case, though, that is 3 on this side and 3 on that side. That is a tie. So that's another way you can get a no change. In this case, there really is no side with more gas molecules than the other. You could also use Le Chatelier's principle and kind of like an experiment you did before the other day, where you have some different colors to help you even decide whether or not something is going to be exothermic or endothermic. So let's say I had this reaction and this side was red and this side was blue. And let's say I increased the temperature and I saw the reaction tube turn blue. But then I decreased the temperature and I saw the reaction guide turn red. Is this exothermic or endothermic, this reaction? Well, let's work through it. I increased the temperature, right? So that is like adding. Adding means it has to go away. And it ended up blue. So it ended up blue. So it had mean the heat was over here, right? When I increased it. Now, does my other one agree? I hope so. When I decrease the temperature, it turned red. When I decrease it, it's like removing it, which means it had to go towards the side I decreased. That would all mean that my heat and energy is on the reactant side, and this means that this reaction should be. Use your observations. And if you throw your test tubes on ice or throw your test tubes in a hot water bath and sort of see changes in colors, if you have that ability to see that in the reaction, you can actually determine if it's exothermic or endothermic by your observations. By the way, both observations agreed with each other, and that usually should happen as well. Any questions on Le Chatelier's principle there? Okay. So this is what we talked about, obviously changing our concentration and changing our volume and our pressure. We talked about, again, exothermic and endothermic, and we did earlier, again, it is really temperature as the only thing that changes that value of the equilibrium constant. And really, when you're doing temperature, it's important to figure out exothermic or endothermic to help you which way is going to basically change. So let's take a look at this one. Since we have the answers, we'll just walk through each of these and see how we get the 3. In this case, we're looking for how many of these changes would cause us to go to the reactant side. So we basically want to see which ones will cause a shift to the left. If I removed CO, CO is over here. If I remove CO, it would actually shift to the right, which would not do that what we need. If I add O2, O2 is a product, which means that we have more products. That would allow the reverse reaction to occur. So that would do it. If I remove CO2, which is over here, that's like I have a hole on this side. That's going to also allow the product reaction and the reverse reaction to occur. So that would shift it in that direction. And increasing the pressure by decreasing the volume. Decreasing the volume means I need less gas molecules. So we have 2 gas molecules over here, and we have 3 total over here. So smaller volume means it will shift to the smaller number of moles, and this guy will do it. So 2, 3, and 4 are the 3 things that will actually cause it to shift to the reactant side. Any questions on that one there? Okay, so here. One method is this endothermic reaction. We want to know which of these changes would cause the H2 to go down. The only way to cause H2 concentration to go down is overall the reaction needs to shift to the left, right, away from H2. So if we added water in this case, which is here, it would actually go away from it and it would shift the equilibrium to the right, which would cause H2 to increase. So that is not good. By the way, water will affect the equilibrium here because water is in which state? It is in the gas state. Yeah, so water in the liquid state won't, but water here in the gas state will because it is in that gas state. The volume of the container is doubled, so that means my volume goes up. I need more gas molecules. Left-hand side is 2 gas molecules. Right-hand side is 4. This would also cause the equilibrium to shift to the right, which will not help me out in my H2. CH4 is removed, which means I have a deficient side over here. That's going to cause the reverse reaction to occur. So that is definitely going to do what I need, which I'm assuming the last one will not. Temperatures increase. It's endothermic, which means heat is a reactant. So when we increase the temperature, we'll cause the equilibrium to shift away. And that will cause it to shift that way, which would make more H2. So in this case, it is number 3 that is actually the one that will cause us to actually have less H2. Any question in those cases there? Okay, so let's see here. The value of K, as we talked about, if it's large, means you mostly have products. If it is small, you really mostly have reactants. And again, there are some times where even though it is a reversible reaction, the value is so large one way are very small in the other way. It is essentially a one-way street. But even in a reaction where you have a really large equilibrium constant or a very, very small equilibrium constant, there's always a reverse reaction happening, even if it's super, super small. So even in a really small one where it's essentially all going that way, and there is a little bit of it kind of heading in the opposite direction. So otherwise it wouldn't be a reversible reaction, but there are proportions of it where it's sort of unequal in that sense, favors one way or the other. All right. Now you can use the equilibrium constant if you know the equilibrium values for other things. You can find a missing concentration. Remember that when you do go into this expression of products over reactants, they have to be equilibrium concentrations, obviously, to go into that expression to do it correctly. All right, so obviously in this case, if the equilibrium lies to the right, we would expect more products and we would have a large value of K. And obviously if it lies to the left, that is more reactants, which means we should have a small value of K. So in this case, if we look at this, come back. This reaction here, we have the equilibrium constant given to us, and these are actually equilibrium concentrations. Even in, they don't give it or say that, but they are. So in this case, we could use our equilibrium expression, which would be our products, which would be HI in this case, and we would square it because of the 2 that is here, divided by the concentration of H2 and I2, and that would equal 50 in this case. In this case, it gave us a concentration of I2, and they also gave us a concentration of HI. So in this particular case, we could put our values in. This would be 5 times 10 to the minus 1 squared divided by H2, and our I2, which is 1.5 times 10 to the minus 2, would equal 50. We're basically going to take both of these guys and multiply it to the other side. And when we do that, we will end up with 5 to the minus 1 squared on the left, 0.25, equals basically 50 times the H2 concentration times 1.5 times 10 to the minus 2. We are then going to basically divide both of these guys back to the other side. So we could solve for our H2 concentration. So we'll divide that by 50. We'll divide that by 1.5 to the minus 2. Going to give us an H2 concentration of what we see on the bottom there, 0.333 and 3s. In this case, everybody has 2 significant figures, so probably 2 sig figs is appropriate here. 0.33 molar. That obviously is the scientific notation of 0.33 molar. Any questions on that one? So this is a kit, yeah. Yeah, so we're gonna actually we're gonna do it right now. An example, which I think will answer your question. First off, any other questions on this one? So we'll steal this equation here and do a problem. So the type of question like that was on the post lab and stuff like that is actually what you're given is not equilibrium concentrations. You're actually given initial concentrations. And when you're given initial concentrations, you actually have to do some calculation to actually calculate what the equilibrium concentrations are. And the way that we typically do this, which after this, you'll probably never see it until 1B again, but that's all you do in 1B. I don't know why they do it in this class, but this is what is sometimes referred to as ICE tables. You might see it in 1A if somebody teaches you limiting reagents with ICE tables, but probably they won't. So you'll see this a lot in 1B, but we use ICE tables. And what ICE stands for is I stands for initial concentrations. C is the change. And E stands for what everybody's concentration is at equilibrium, basically. So let's say we had a problem like the equation we just saw, which was H2 plus I2 gives us 2HI, and they gave us our K value there of 50. And let's just say that initially we started with an initial concentration of H2 of 0.5 molar, and we'll do I2 as also initially 0.5 molar. So these are really initial concentrations. So what we would do is we would actually take the equation. You obviously, like normal, want to make sure the equation is balanced. We would do an I, and again, I stands for initial concentrations. So we would put our 0.5 here, do our 0.5 here. Now, in this particular problem, they didn't mention anything about the products. So it is very safe to assume that you're starting with nothing on the product side, so 0. To answer your question, what you were given were 0. That's why there were zeros, because there actually were initial concentrations and not equilibrium concentrations. Otherwise, if you try to throw that into your expression, 0 on top's not good, right? When you try to divide. So that's really why they were nice enough to tell you there's zeros. But in a lot of problems, they actually will not even say anything about the products in a problem like this. And it's safe to assume that it is going to probably be 0 to begin with. Because it's actually 0 to begin with, it is also safe to assume that this reaction pretty much has no choice but to basically head in this direction, right? And that is because there's only reactants. So there's no other direction it could go other than to make products. That's also really important for the change part of the table. And that is because if I am heading to the product side, my reactants, my H2 and my I2, should their concentrations increase or decrease? They should decrease. They should be going down. And the way we represent decreasing in an ice table is with minuses, basically negative signs or minuses. And our HI, which is our products, should start to increase with time, right? As we start making them. And the way we represent that in the ice table is with pluses, basically. Probably 9 times out of 10, very rare occasion it'll go the other way, but maybe even more than 9 times out of 10, your negatives will be on the reactant side and your pluses will be on the product side. We represent the change part usually as the unknown we're looking for, and we usually use the letter X to represent basically what we're looking for. So we will do minus X here, and it's really important as well that we're actually going to take the coefficients into account to make sure the stoichiometry is all good. And because the coefficient here is 1, that's why it's basically 1X here. Coefficient here is also 1, which means this would be minus X. Now on the product side, it should be increasing. So this is going to be plus X, but we do need to take the coefficient into account. This would be plus 2X in this case. Any questions on the change part? Really, really important that you take the coefficients into account when you do the change part. Otherwise, you pretty much did the wrong mole-to-mole relationship. The stoichiometry is going to be all off. So really important when you do that part. Now, in this table, what we do now is we basically just bring this down, or it's going to bring everything straight down. So 0.5 minus X, 0.5 minus X, and 2X. This line here represents the equilibrium concentrations of everybody. There is one thing missing for us to figure that out, which is X. So what we need to do is actually find what X is. To do that, we're going to use our equilibrium expression. So in this case, K would equal, just like it did on the previous one, HI squared divided by H2. And again, we do need to square the top one because of the coefficient as well, will equal 50. So to allow us to solve for X, we're basically going to take our equilibrium line and we're just going to stick everybody into the appropriate part here. So if I did that, up on top, I would have 2X that's squared from this guy, divided by 0.5 minus X for this guy, times 0.5 minus X for that guy, and that would all equal 50 at this point. Any questions on that there? At this point, you could do some fun math. You could quadratic it out. You could use a successive approximation, but nobody in this class should be doing that. When you go to 1B, you'll do that, but not here probably. So if you could recognize it, it is like a perfect square. I'm just going to put a big old square root on both sides there and kind of work it that way. When I square root the left-hand side, I'm going to get me a 2X up on top. I'm going to also give me a 0.5 minus X on the bottom. And the part I usually forget, which is actually take the square root there, 50. We'll take the square root of 50. We'll call it 7.07107. At this point, what we're going to do is take the bottom guy here and multiply it to the other side. So we're going to move that whole thing over to the other side. That's going to give us a 2X is equal to 0.5, which gives us 3.5355. And that will then be minus 7.07107X. So basically, I'm just going to factor in that 7.07 into each of the things in the parentheses. I want to combine my X's, so I'm going to bring this guy to the other side by adding it to the other side. That 5355. Yeah, so I'm going to divide that to the other side. And after doing all that fun math here we go. Yeah, we'll call it an X value of 0.390 in this case. First off, any questions on the math here? Now that X value is really the change that's going on in this reaction. And that X value that we just solved for right here is this X value, is this X value, and it's this X value. And that's what we're going to use to be able to figure out what everybody's equilibrium concentrations are. So the last thing that we would want to do is actually take that X value and actually put it into that line. So the concentration here of H2 based on our equilibrium line is 0.5 minus 0.390. That gets us 0.5 minus 0.390, 0.110 molar. Our I2 actually will be identical. It will be 0.5 minus 0.390, 0.110. And our HI from our equilibrium line is actually equal to 2x. So we would take 2 times 0.390. It says 0.780. And these in the box here would represent our equilibrium concentrations of each of these guys. Question on that there. By the way, since we now have the equilibrium concentrations, I could take each of those values and put it back into here. And I should get approximately, which is what you get, about 50.2, 50.3, and it should be in the same ballpark. So it's a good way to check to maybe make sure nothing went wrong in the calculation. If you're significantly off and it's not more than rounding, you might want to take a look. Question on any part of that there. So to answer your question, the post-op question, what was given were initial concentrations. You actually had to do a nice table like this, and you had to solve it this way. There are many ways you could solve a problem like this. You could use a quadratic formula, which is done before. There's stuff known as successive approximation, stuff like that. But in this class, if it is a nice table problem like this, it's a perfect square in most every case, because we don't really teach that part of it in this class. Yeah. Other questions on that? All right, then let's try one here. Let's try let's do 2A plus 2B. Let's say we had K equals 10, and we'll say initially we had 0.1 molar of A and 0.1 molar of B. Why don't you give that a try? What is everybody's equilibrium concentrations? Actually, I'm sorry here. Let me put the T's here. So I don't make it a giant math problem for you. So we're basically given the initial concentrations of these guys. So we'll put them into our table. And once again, we weren't given anything about our product, so we'll safely assume that it's 0. This one will come out very similar to the last one. So minus X because the coefficient is 1, minus X because the coefficient is 1. And once again, here we will have our plus 2X in this case. 0.1 minus X, 0.1 minus X, and 2X. In this case, our K would equal our AB squared divided by our A2 and our B2 equals 10. Once again, we're going to take our equilibrium line and basically insert it into here to figure out our X. That will again give us 2X squared, our 0.1 minus x, 0.1 minus x, and our 10. Again, it is a kind of perfect square there on both sides. That will give us 2x up on top, 0.1 minus x, and a little square root action of 10 there. 3.16228. Just like before, we're going to multiply this to the other side. That gives us 2x is equal to 0.316228 minus 3.16228x. Just like before, we will combine our x's by moving this guy to the other side. That should give us 5.16228x, 0.316228. Doing a little dividing action at this point. It gives us an x value of 0.0613. Any questions on any of that there? At this point, once again, this x value is every single x we see here on the equilibrium line. So to figure out the equilibrium concentration of A2 would be 0.1 minus 0.0613. So 0.1 minus 0.0613 gives us 0.0387. B2 will come out the same, 0.1 minus 0.0613. And here, though, our AB will be 2x, which would be 2 times 0.0613. And that's going to give us 2 times 0.0613, 0.123, we'll call it, molar in this case. So that will once again give us our equilibrium. Stick it back into the expression, and you should get about 10, which you do about 10.03, I think. Can we put it back in? Any questions on any of that there, or how to do these here? Okay, so let's talk about a specific type of equilibrium. And this is what is known as KSP. KSP is known as a solubility product, and it actually is an equilibrium constant for things that are insoluble. So if you remember back in like your solubility rules, for example, if you take silver and combine it with chloride, you will get a solid. Even though this thing is insoluble in solution, it is actually sets up an equilibrium, and a little bit of it will break apart into its actual ions. And it sets up a KSP, and KSP, because they really are for insoluble things, are very small values usually. And because they're very small values, that means that we mainly have really our reactants at equilibrium, but we do get a little bit of our products that will break apart. Now, we could write our KSP expression for this, which would be the concentration of silver times the concentration of chloride. Once again here, because the reactant is a solid, it would not be included. And pretty much all KSP reactions are the same. It is always solid on the left and aqueous ions on the right, which means when you do write your KSP reactions, it's pretty much just products. There's no reactants usually involved because they're usually all solids. When we do KSP type problems, you can also do an ice table for a KSP if you needed to. So for example, if you had your silver chloride, you could do your initial change in equilibrium. The difference is we would start with zeros here. We would then do plus S and plus S, and this would be S and S. You may be wondering, why am I using S here? Because it's really the thing that you should use. S stands for what is known as the molar solubility. It is a fancy way of saying molarity, basically. It's basically the molarity of each of these guys. You could still use X if you like, so you could use X instead. But in like 1B, when you really learn about this stuff, you usually will use S for molar solubility, but you can still use X. It's doesn't matter what letter you use. So we would do the same thing. We would then put that into our KSP expression, and we would solve obviously for each of those guys at equilibrium. So in this case, this is our Bi2S3 breaking apart into its ions. Like a normal equilibrium, we still take our coefficients as our exponents. And again, you can see this guy not included because it is a solid when you look at it there. So for example, if we look at this here, this lead-2 chloride, and it tells us that the concentration has been determined in solution, we can actually do like an ice table here with our lead-2 chloride, which would break apart into lead and a couple of chloride ions. Now, initially, this is 0 and 0. The change would be plus X. I'll use X here. Again, you can use S if you like. And at equilibrium, we would have X, and that should be 2X there, by the way, because of the coefficient. Should be 2X. Why am I not writing anything on this side? It's a solid, it's not included, so don't put numbers there. You don't need to worry about it. That is really technically where the negative part is, even though we don't really have to worry about it in this calculation. That's still where like our minus X's would be and all that kind of stuff. But because it's a solid, it's actually not included. If we put this into our KSP expression, it would be the concentration of lead-2 times the concentration of chloride that is squared. In this case, we actually don't have the KSP. If we did, we could actually solve for X. What X is, they told us that the lead-2 concentration is equal to 1.6 times. And since lead at equilibrium equals X, so we do have everything that we need. We know that the KSP in this case would be 1.6 times 10 to the minus 2 times 2 times 1.6 times 10 to the minus 2, and we still need to square it. So we actually can put our values in there. And if we do that, we should end up with what's on the bottom there, hopefully. So 2 times 1.6 minus 2, we'll square it. Minus 2 will give us 1.6 times 10 to the minus 5 as our KSP value in this particular case. So you can actually use the ice table to help you figure out, you know, how things are. Do you really need an ice table on this one? You don't, if you understand molarity and how it works. You know, this is again a 1 to 2 relationship, so that's really why we are multiplying by 2 here. It's the same idea as we talked about with molarity of ions in this case. Any questions on that one there? This, by the way, would be our KSP. This would be the solubility or molar solubility of lead-2 in that solution. What we would get for this part here, the 2 times that number, would be the molar solubility of chloride. Let's take a look at one last one here to finish it up. So let's say we did have our silver chloride here. And again, it would break apart into a silver ion and a chloride ion. And we're looking for the solubility. So we'll look for the molar solubility in this case, which is really S, and that is molarity, basically moles per liter. So in this case, the only thing given to us is the KSP. And we could write our KSP expression like we did earlier, which was our silver times our chloride. And it would equal 1.6 times 10 to the minus 10. So if we did our ice table, once again, we're not going to worry about this guy because he's a solid. We have nothing to begin with here, so we'll put zeros. Our change, once again, not worrying about this guy. This will be plus X and plus X because it's on the product side, should be increasing, which means at equilibrium, again, not worrying here, gives us X and X. Just like we did with the other ice table, we're then going to take these guys and basically put it into our expression. And when we do that, that will give us x times x is equal to 1.6 times 10 to the minus 10. That is an x squared is equal to 1.6 times 10 to the minus 10. A little square root action on both sides there. Will give us square root of 1.6 to the minus 10. Will give us 1.3 to the minus 5 as our x value. So this is really done the exact same way as we did the other ice table. The only difference is because it's a KSP, there's nothing on the reactant side, basically. This value is what X is. In this case, that is what the concentration of silver would be at equilibrium. So the concentration of silver molar solubility would be 1.3 times 10 to the minus 5 molar. For chloride, the solubility would also equal X. So the chloride's concentration at equilibrium would be 1.3 times 10 to the minus 5 molar. What would be the solubility of the silver chloride at this point? It is we'll just take silver, a 1-to-1 relationship, which means the concentration or solubility of silver chloride is also 1.3 times 10 to the minus 5. And again, that's because it's all a 1-to-1 relationship. When you do a KSP problem, and like technically people use S's, when you do solve for X or S or whatever letter you use here in this type of calculation with KSP, that value that you get here is really the molar solubility of the entire thing, and in this case. So usually when you solve for X, it is usually the molar solubility or moles per liter of the entire compound. Any questions on that there? All right, that wraps up this chapter and this